This video is for those of you who might be going back to school and taking a calculus course. Let's start with limits. So let's say we have some function f of x, and it's equal to x squared minus 4 over x minus 2. What is the limit as x approaches 2 of that function? So what exactly is a limit? What does it do? So basically what this question is asking is, as x approaches 2, what does the y value, or what does f of x approach? Now, one of the first things you could try is direct substitution. If we plug in 2 into the function, it's going to be 2 squared minus 4 over 2 minus 2. 2 squared is 4. 4 minus 4 is 0, and 2 minus 2 is 0. 0 divided by 0 is undefined, so that won't help us. So what we can do instead is we can plug in a number that is very close to 2. Let's try 1.9. So let's find the value of f of 1.9. So that's going to be 1.9 squared minus 4 over 1.9 minus 2. (1.9 squared minus 4), that's negative 0.39. 1.9 minus 2 is negative 0.1. When you divide these two, you're going to get positive 3.9. Now what if we plug in a number that's even closer to 2? So let's say 1.99. What's going to happen? Well, let's see what we're going to get. So 1.99 squared minus 4, that's negative 0.0399. And 1.9, this is supposed to be a 2, by the way, not a 4. So let me just fix that. 1.99 minus 2, that's equal to negative 0.01. And so let's divide these two numbers. And this is equal to 3.99. So here's a question for you. As x gets closer to 2, what happens to the y value, or basically the value of the function? Notice that it gets closer and closer to 4. 3.99 is a lot closer to 4 than 3.9 is. So therefore, we can make the conclusion that the limit as x approaches 2, as we get closer and closer to 2, the value of this function approaches 4. And so this direct substitution technique can always work. If you can't plug in the number directly, you can plug in a number that's very close to this number. And as you'll see, the limit approaches a certain value. Now let's go back to the first problem. It turns out that there's another way in which we could get the same answer. So even though we can't plug in 2 directly because it's going to be undefined, we can simplify the expression. We can factor x squared minus 4. And it's a difference of perfect squares, so it's going to be x plus 2 times x minus 2. So notice that we can cancel a factor. We could cancel x minus 2. And so what we have now is the limit as x approaches 2 of x plus 2. At this point, we can use direct substitution. We're no longer going to have an undefined value. So if we replace x with 2, it's going to be 2 plus 2, which is equal to 4, which confirms our previous answer. So sometimes there are certain algebraic techniques that you can use to evaluate this limit, other than using direct substitution with numbers that approaches 2. Now that technique always works, so it's a good fallback method. But on a test, you may have to show your work, so you need to also learn the analytical methods with it as well. So I'm going to give you 4 problems, and I want you to evaluate the limit. So let's start with this one. What is the limit as x approaches 3 of x squared plus 5x minus 4? feel free to pause the video and work on this example. Now in this problem, we could use direct substitution. If we plug in 3, we're not going to get an undefined value. We're not going to get a 0 in the denominator of a fraction. So always check to see if direct substitution will work. So this is going to be 3 squared plus 5 times 3 minus 4. 3 squared is 9, 5 times 3 is 15, and 15 minus 4 is 11. 9 plus 11 is 20. And so this is the answer for this example. Now what about this one? What is the limit as x approaches 3 of x squared minus 8x plus 15 divided by x minus 3? Now if we try to use direct substitution, if we plug in 3 minus 3 is going to give us a 0 in the bottom of the fraction, which will make it undefined. So therefore we don't want to do that. Let's see if we could factor the trinomial on top. So what two numbers multiply to 15 but add to negative 8? So we know that 3 times 5 is 15. But we need it to add up to negative 8. So we need to use negative 3 and negative 5. So therefore, x squared minus 8x plus 15 is equal to x minus 3 times x minus 5. And now we can cancel x minus 3. So we're left with the limit as x approaches 3 of x minus 5. By the way, some teachers will require you that they want you to rewrite the limit expression until you replace x with 3. Some teachers will take off points if you don't rewrite the limit expression. So I just want to give you that warning so you don't lose points on a test. So now let's plug in 3. So it's going to be 3 minus 5. At this point, we don't need to rewrite the limit. And this is equal to negative 2. And this is the answer. Now what about this one? What is the limit as x approaches 4? Given a complex fraction, 1 over x minus 1 over 4 divided by x minus 4. Now in this case, we can't factor. There's nothing to factor in this example. But whenever you have a complex fraction, here's my recommendation. Multiply the top and the bottom by the common denominator of the smaller fractions that you see. So in this case, let's multiply the top portion of the fraction by 4x and the bottom by 4x. On top, let's distribute 4x times 1 over x. The x variables will cancel, leaving behind 4. And don't forget to rewrite the limit expression. So this is positive 4. And then if we multiply 4x by 1 over 4, this time the 4's will cancel, leaving behind negative x. On the bottom, you don't need to change anything. Don't distribute the 4x, just leave it the way it is. Notice that 4 minus x and x minus 4 are very similar. They're not exactly the same at this point, but there's something that we can do in the next step. Let's take out a negative 1 from 4 minus x. Let's factor it out. If we factor out a negative 1, negative x changes to positive x, and positive 4 will change to negative 4. So notice that now we can cancel x minus 4. So we're left with the limit as x approaches 4 of negative 1 divided by 4x. Now we could substitute x with 4. And we don't need to rewrite the limit expression at this point. So it's negative 1 divided by 4 times 4. And so the answer is negative 1 over 16. So this is it. Now let's confirm that negative 1 over 16 is indeed the answer to this problem. So if you're not sure, you can always plug in a number that's close to 4. You can't plug in 4 directly because 4 minus 4 is 0. But let's plug in a number that's close to 4. Let's use 4.1 and then let's use 4.01. So let's find the value of f of 4.1. So that's 1 over 4.1 minus 1 over 4 divided by 4.1 minus 4. Now 1 over 4.1 minus 1/4. That's equal to negative 0.0060975. And there's a 6 after that. 4.1 minus 4 is just 0.1. And so this gives you negative 0.0609756. So let's keep this value for now. Now let's try f of 4.01. So that's 1 over 4.01 minus 1/4 over 4.01 minus 4. So the numerator has a value of negative 0.0006234. And the denominator is going to be 0.01. So I'm going to put this value up top since I'm out of space on the bottom. So this is about negative 0.0623. Now let's say if we want to go further, if we want to try f of 4.001. I'm not going to write it out, I'm just going to type it in the calculator. So this is going to be negative 0.06248. So notice that it's converging to a certain value. Here it was negative 0.0609. Here it's negative 0.0623. And now it's negative 0.0624. And I'm missing a 0. It's supposed to be a 0 somewhere here. So it's converging to a certain value, which means that the limit exists. Now, negative 1 over 16, if you type this in your calculator and convert it to a decimal, this is negative 0.0625. As you can see, these two answers are very close, even though they're not exact. But as x approaches to 4, as it gets closer and closer to 4, this value is converging to negative 1 over 16, or negative 0.0625. I keep forgetting the 0, but that's supposed to be 0.0625. Let's try one more problem. Evaluate the limit as x approaches 9, given the function square root x minus 3 over x minus 9. Now, if you're not sure what to do, and if you have a multiple choice test, you could find the value of f of 9.01. So that's close to 9. So let's see what this is equal to. So this is 0.16662. So basically, let's say 0.167. So the answer should be close to this value. And if you want a better answer, plug in 9.001 or even 9.00001. The closer it is to 9, the more accurate the answer will be. But if you have a free response test, then you have to show your work. Whenever you have a square root inside a fraction, what you want to do is you want to multiply the top and the bottom by the conjugate of the numerator. In this case, by the square root of x plus 3 as opposed to minus 3. So don't forget to change the sign. And whatever you do to the top, you must also do to the bottom. Now on the numerator, we're going to FOIL. The square root of x times the square root of x is simply x. And then here we have positive 3 square root x. And then let's multiply negative 3 by root x. So that's negative 3 square root x. And then negative 3 times 3 is negative 9. Now, what I would recommend is not to FOIL these two. Keep it the way it is. It's going to work out nicely if you don't FOIL x minus 9 with the square root of x plus 3. And let's rewrite the limit expression. So now we could cancel positive 3 square root x and negative 3 square root x. 3 plus negative 3 adds up to 0. So what we have left over is x minus 9 divided by x minus 9 times the square root of x plus 3. So notice now that we could cancel x minus 9. So once you get rid of this x minus 9 factor, you can now plug in 9, because this, it prevents us from doing so. It will give us a 0 in the bottom. So once that's gone, now we can use direct substitution with the exact value. So once we plug it in, we don't need to rewrite the limit expression. So all of this is equal to 1 over the square root of 9 plus 3. And the square root of 9 is 3. And 3 plus 3 is 6. So the final answer is 1 over 6. That's the exact answer. Now, 1 over 6 as a decimal is basically 0.16666 repeated. So you can say 0.16, which is basically 0.167. It's close to that. So these two values, they're in harmony with each other. So whenever you're evaluating limits analytically, see if you can either factor, or if you have a complex fraction, multiply the top and the bottom by the common denominator, or if you have a fraction with a square root symbol inside of it, multiply the top and the bottom by the conjugate of the square root factor. Now the next thing that you need to be able to do is you need to know how to evaluate a limit graphically. So let's say if you want to find these four things. What is the limit as x approaches negative 3 from the left side? So that's a one-sided limit. And what is the limit as x approaches negative 3 from the right side? The right side is indicated by the positive superscript. And what is the limit as x approaches negative 3 from either side? And finally, what's the value of f of negative 3? So these are common questions that you might see in a test when evaluating. I lost my the cat caught my tongue. When evaluating limits graphically. So what is the value that f of x approaches as x approaches negative 3 from the left? So first, identify the value where x is negative 3. So that's this point here. Now, if we follow the function from the left as we approach an x value of negative 3, we're going to be on this curve. So we're approaching negative 3, and notice that the y value there is 1. So therefore, as x approaches negative 3 from the left side, f of x approaches 1. Now what about from the right side? So anywhere along this vertical line, x is negative 3. So we're going to approach that x value starting from the right side. And so it's going to take us to this vicinity where the y value is 2. So as x approaches negative 3 from the right side, f of x is equal to 2. Now what about the limit as x approaches negative 3 from either side? If the left side and the right side, if they differ, then here's something important that you need to know. The limit does not exist. Unless these two match, the limit will not exist. Now what about the last one? What is the value of f of negative 3? So when x is exactly negative 3, what is the function value? So in this case, you need to look for the closed circle at an x value of negative 3. And basically, that closed circle has a value of -1 on the y-axis. So f of -3 is equal to -1. Now, whenever the limit doesn't exist, you have a certain type of discontinuity. This particular discontinuity is known as a jump discontinuity because there's a disconnect in the graph. A jump discontinuity is also known as a non-removable discontinuity. So let me give you some more questions relating to this topic. So what is the limit as x approaches -1 from the left side? And what is the limit as x approaches -1 from the right side? Now, once you find those two values, I want you to find the limit as x approaches -1 from either side, and then find the value of f of -1. So anywhere along this vertical line, x is equal to -1. So as we approach an x value of -1 from the left side, notice that the y value approaches -3. Now, as we approach it from the right side, the y value is still -3. So notice that the left side and the right side have the same value. Therefore, the limit exists, and it's equal to -3. Now, what about f of -1? So along this line, you want to look for the closed circle, and here it is. And it has a y value of -2. So f of -1 is -2. Now, this type of continuity, or rather discontinuity, where the limit exists, but it doesn't equal to the function value, is known as a hole. And that type of discontinuity is known as a removable discontinuity. So that's simply a hole. Now let's talk about another problem. What is the limit as x approaches -2 from the left side? And also, what's the limit as x approaches -2 from the right side? And also from either side? And finally, what's f of -2? So as x approaches -2 from the left side, so here's where x is -2. As we approach from the left side, notice that the graph goes higher and higher and higher. So therefore, it approaches positive infinity. Now, as we approach -2 from the right side, notice that it goes down towards negative infinity. And these two, they don't match. So therefore, the limit doesn't exist. Some teachers will also say that infinity, because it's not a specific number, they will define it as the limit not existent too. So just keep that in mind. Now, what about f of -2? Now, there's no closed circle along that vertical line, so therefore, this value does not exist either. You could say it's undefined, because typically, whenever you have, let's say if you were to graph 1 over x minus 2, you're going to see a vertical asymptote at x minus 2. And at 2, if you plug it in, you would say it's undefined, because f of 2 will equal 1 over 0. So whenever the function doesn't exist due to a vertical line, you could also say that it's undefined, because that's why you have a vertical asymptote, typically because there's a 0 in the denominator. So just keep that in mind. Now let's try one more set of problems. What is the limit as x approaches 1 from the left, 1 from the right, 1 from either side, and also let's find the value of f of 1. By the way, you need to know what type of discontinuity this represents. That's known as an infinite discontinuity, and it's also a non-removable discontinuity. Now let's move on to the next problem. As x approaches 1 from the left side, notice that the y value approaches 1. And as x approaches 1 from the right side, the y value is still negative 1. So because these two are the same, as x approaches 1 from either side, it's going to be negative 1. The limit exists. Now, f of 1 is also negative 1 because we have a closed circle at this point. Even if there were no closed circle, if there was a straight line, if we didn't have an open circle, it would still be negative 1. Now, whenever all four of these values match up, the function is continuous at x equals 1. Whenever there's a mismatch, it's discontinuous. Either it could be a hole, it could be an infinite discontinuity, or it could be a jump discontinuity. But when all four of these values match, then we can say that the function is continuous at x equals 1.